Okay, so now that we've discussed the basic concept of partial derivatives, how it's connected to the gradient, and keep in mind, gradient is not a factor. Its gradient is a vector. Okay, now that we've discussed that, let's go more into detail about the significance of this gradient vector. So continuing with our example here. So let's say I will draw this. I will draw the coordinates again here. So let's say we have, again, we have this plane here. This is the plane here. And we have x0, y0. Right? So this point results in z0 here. So then we see that basically as z increases, it's climbing this way. In this particular example, right? Z increases in this fashion, right? So basically, we can say, let's say, I'm going to use a different color here. So let's say this line here is level curve, okay? Z equals to Z0. So meaning that along this line on the plane, the Z values are all Z0, same height, same elevation, right? So then when this level curve gets translated down here, then let's say it should be like, and it's going to pass through this point, right? So let's say it's going to be like this line here. So this is our level curve. Level curve Z equals to Z0, okay? And then basically the gradient vector f of x0, y0, which equals to the vector, the function partial derivative f of x at x0, y0, and f of y at x0, y0. Basically, this vector here is perpendicular. It's obviously, it's got x coordinate and y coordinate, right? So obviously it's a vector on the xy plane. So this vector, by theory, is going to look like that, and is perpendicular to the level curve. It's always perpendicular to the level curve, and I'll explain why in a second. So then visually speaking, what this gradient vector says is that at x0, y0, at this point, the maximum rate of increase in the z value should we deviate from this point just a tiny bit, let's say this way or this way or this way or this way, right? Should we deviate from that point, the direction in which we deviate, that will result in the maximum change, or rather maximum increase in the z value from z0 will be in this direction, in the direction that is perpendicular to the level curve. Okay, and that's what this is basically saying. So basically, the level curve is basically f of x, x0, y0. So this is a partial derivative. This is a value times x minus x0 plus f of y, x0, y0 times y minus y0 equals to 0. And this is just, in calculus, this is just a classic way to write the equation of a line. And you can see that this is basically This is like saying arbitrarily, like if we plug in some numbers, this is like saying, okay, this is equals to 3 times x minus 2 plus 4 times y minus 1, right? Meaning, where 3 refers to this partial derivative, 2 and 1 are the coordinates, x0, y0, and 4 is the partial derivative with respect to y. So you can see that this is a equation of a line, right? So then this is the equation of the level line, the level curve rather. This level curve, the equation of this level curve is given by this here. And whereas this and this are the x and y values of the vector, of the gradient vector here. Okay, so that is the visual or geometric concept of the gradient vector. When you evaluate it, when you find out what this gradient vector is, it refers to a vector on the xy plane here that if you move in that direction for x and y, it will give you the maximum increase in the z value, in the elevation of z value. And coincidentally, this gradient vector is also perpendicular to the level curve of z equals to z0. So next, I'm going to talk about why the gradient vector is perpendicular to the level curve.